Today we're going to talk about Lesson 12, which is prime and composite numbers. So we're going to start off defining both of these. Let's start off with composite numbers. Composite numbers is any positive integer that can be divided by a smaller positive integer other than 1 in itself. In other words, it has more than 2 factors. An example of a composite number is the number 6. The number 6 has other factors or other numbers that I can multiply together to get 6 instead of just 1 and 6. We think about the two numbers 2 times 3. So 6 would be considered a composite number. We're going to go through the lesson today, and we're going to talk about different ways that we can determine if a number is a composite number. A prime number is a number that is a whole number that is greater than 1. Remember, whole numbers are 0, 1, 2, 3, 4, 5, and etc. That cannot be exactly divided by any other whole number other than itself and 1. In other words, it only has 2 factors. An example of a prime number is 7. The only 2 whole numbers that multiply together to give me 7 are 1 times 7. So that would be an example of a prime number. So let's talk about some special cases. We often wonder, is the number 1 prime or composite? The answer to that is it's neither. It's not considered prime or composite. It's a special case. Well, what about 0? Is it considered prime or composite? No, it is neither prime nor composite. It is also considered a special case. So when we think about the numbers 1 and 0, we do not consider them prime or composite. What about the number 2? Yes, it would be considered prime because it only has 2 factors that multiply together that are whole numbers, that when I multiply them together give me 2, and that's 1 and itself. So 2 is a prime numbers. Prime numbers are very important in math, and as you're teaching this, you're going to emphasize that prime numbers are often referred to as the building blocks of whole numbers. You're going to see that as we talk about factorization in a moment. All right, so let's think about the numbers from 13 to 20, and we're going to identify it as prime or composite. I've identified 13 as a prime number because the only numbers that when I multiply together, and again I'm thinking about whole numbers that give me 13, are 1 and itself. So we're going to consider that a prime number. 14, 15, 16, 18, and 20, these are composite numbers because there are other factors other than 1 in itself that gives me 14. We can think of 2 times 7. If we're thinking about 15, we can think of 3 times 5. 16, 2 times 8. 18, we have 3 times 6, 2 times 9. So there are other factors other than 1 in itself. Other numbers that are prime between 13 and 20, we can think of 17 and 19. These are prime numbers because only 1 times 17 gives me 17 when we're thinking about whole numbers being multiplied together. And the only factors of 19 are 1 times 19. So those are the ones that are identified as prime and composite. So again, some examples of some prime numbers are 2, 5, and 7. These are just examples of numbers who only have 2 factors, 1 in itself. 1 times 2 is 2. 1 times 5 is 5. 1 times 7 is 7. How do we tell if a number is prime? Are we supposed to just be able to look at any number and know that it's prime? There is a prime number test out there. Several ways that you can determine if a number is prime. One way to determine if a number is prime is to check the divisibility of every prime number less than the given number. So, if I wanted to determine if a number is prime, and we will do this in a minute, of the number 15, then I would look at all the prime numbers less than 15, and I would check my divisibility rules that you learned in the previous lesson, and I would check to see if it had any other factors. That's one way that you can test if a number is prime. Another method is just to make sure that it doesn't have any other factors other than 1 in itself. And again, here we're going to be applying some divisibility rules to see if there are other factors other than 1 and that number. We want to make sure that we use the divisibility test. We don't want to have to drag out our calculator every time we want to see if a number is divisible by another number. These divisibility tests come into play not only in determining if something is prime or composite, but in doing lots of math. So we really want to teach our students these divisibility tests, and that'll be something that they carry on throughout their higher education when they go into higher math courses. There is a trick to determine if a number is prime. One of the tricks is to take the square root of a number, and then you're going to check all of the numbers up to that square root. And we'll see this in just a minute. You only have to check the numbers up to the square root of that number. And if you find one that it's divisible by, often again using those divisibility tests, then you know if a number is prime or composite. So let's look at some examples. The number 43,101. Why is it considered a composite number? We're going to use one of our divisibility tests, and I'm going to add up all the digits of that number. 4 plus 3 plus 1 plus 0 plus 1. That equals 9, and 9 is divisible by 3. That means that 43,101 is divisible by 3. So because I have proven that it's divisible by some number other than 1 in itself, we consider that a composite number. 24,638 is very easy to see that it's a composite number because it's even. We know that any even number is divisible by 2, and therefore it is a composite number. The third example is 53. Here's the divisibility trick that we were talking about in the previous slide, where if I take the square root of 53, I get approximately 7 point something. And so what I'm going to do is I'm going to check to see if 53 is divisible by all the numbers from 2 to 7. So 2, 3, 4, 5, 6, or 7. Well, 53 is not divisible by 2. It's not divisible by 3. It's not divisible by 4, 5, 6, or 7. Because I only have to check those factors, I can tell that 53 is a prime number. Meaning, again, that only factors that 53 have, whole numbers that I can multiply together to get 53, are 1 times 53. All right, let's look at a larger number, 421. Again, we can take the square root of 421, you get 20.5. So you check all the numbers from 2 to 21 to see if 421 is divisible by any of those. If you check those factors, you'll see that 421 is not divisible by any numbers 2 through 21. Again, we're going to use those divisibility rules. For instance, I can take 4 plus 2 plus 1. I can add the digits of 421, and I get 7. 7's not divisible by 3, therefore 421 is not divisible by 3. If I look at the last 2 digits of 421, I look at the number 21. 21's not divisible by 4, therefore 421 is not divisible by 4. We know that it's not divisible by 5 because it doesn't end in 0 or 5. It's not divisible by 6 because it's not divisible by 2 and 3. And I know it's not divisible by either because it's not even, and we've already tested for 3. So those are, again, those divisibility rules are going to come in handy as you go through this lesson. We can look at 667. When you take the square root of 667, you get approximately 25. So what we're going to do is we're going to check to see if 667 is divisible by any numbers 2 through 25. And as you're going through these and you're checking them, you're going to see that you're going to almost think it's prime, but when you get to 23, 667 is divisible by 23. So it actually ends up being a composite number. But by taking the square root and only checking for the numbers up to that square root, it surely takes out a lot of guesswork. I know that if I check those factors, I can determine if it's prime or composite. Let's talk about the sieve of Eratosthenes. the sieve of Eratosthenes. This is a very ancient but efficient algorithm that you can use to find all prime numbers up to another given limit. All right, so let's look at this example. This is an example of the numbers that I've listed from 1 to 200. Here's how you use the sieve of Eratosthenes. To find all the prime numbers up to a given number, you begin by crossing out the number 1. If you remember about the number 1, it is a special case. It is considered neither prime nor composite. So we're going to circle 2. This is our first prime number. And the way this works is you're going to go through and you're going to mark out all of the multiples of 2. So that would be 4, 6, 8, 10, 12, 14, 16. And you just go through and you continue marking out all the multiples of 2. We see that all these numbers are divisible by 2. So of course, these are not going to be prime numbers. And I'm going to continue doing that all the way through. Let's see, that should be 62. And I'm going to put dot, 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 and we're going to go through. And we will mark through all of the multiples of 2. And then I'm going to start with 3. So I'm going to circle 3. That's my next prime number. And then I'm going to go through, and every multiple of 3, I'm going to make sure that it's marked out. So 3, 6, there's 9, so I'm going to mark it out. 12, 15, I'm going to mark it out. Then we're going to go to 18, it's marked out. So then I go to 21, and then I go to 24, it's marked out. And then I go to 27, and I'm going to put dot, dot, dot. So you understand what I'm doing here. I'm going to go through and I'm going to mark out all the multiples of 3. And then we'll just continue on. I'll go with 5, and then I'm going to do multiples of 5. 5, 10, 15, 20, 25, 30, 35, 40, 45, and etc. Everything that you have left is going to be your prime numbers. So I have completed this. We're going to go to the next slide, and I'll show you an example of one that I have completed. So here's what it would look like if I had went through. You can see I started with 2, mark all the multiples of 2, then you go to 3, then all the multiples of 3, then you go to 5, and you keep going to all the multiples of 5, and everything that's not marked out, you keep going until you mark it out. And this is a very easy way of determining which numbers are prime. This is a very ancient algorithm, so it's been used for years. And again, it is very efficient. So let's talk about a factor tree. A factor tree is a great way to take a number and break it up into its factors. You're going to be using this a lot, but every composite number can be written as a product of primes. Now remember, the word product means multiplication. So I can take any number and write it as a product of primes. And so one method that we use to write the prime factorization of these composite numbers is by using a factor tree. So let's take a look at how the factor tree works. But this is based on an idea or a theorem called the fundamental theorem of arithmetic. You need to know what this means. The fundamental theorem of arithmetic states that every composite number can be expressed as the product of primes in exactly one way, except for the order of the factors of that product. And we're about to take some numbers and we're going to break them down into its product of prime using a factor tree. We're going to see in just a minute that the number of 12, its product of primes is 2 squared times 3. That is the only way that I can break up 12 is 2 squared times 3. They're telling me that the only way that I could take the composite number or the composite whole number 12 and express it as a product of primes is by 2 squared multiplied by 3, disregarding the fact that I could put them in different orders. I could say 3 times 2 squared. You're going to see that when we use the factor tree in just a minute for factors of 12, it doesn't matter how we begin to break these factors down. There is only one product of primes for 12. So we're going to end up with the same product of primes regardless of what method we use to get there. That is what the fundamental theorem of arithmetic says. Every composite whole number can be expressed as the product of primes in exactly one way. So let's look at some examples of the prime factorization. We're going to find the prime factorization of a composite number by rewriting the number as a product of two smaller numbers. So when I was talking about writing the prime factorization of 12 in the previous slide, it doesn't matter what numbers that I multiply together to get 12. Some of us might start off by saying, well, 12 is 6 times 2. Somebody else might start off and say that 12 is 4 times 3. It doesn't matter. We're going to end up with the same prime factorization of 12 regardless of what two numbers we choose that are factors of 12. When we're doing the prime factorization tree, we begin with any two numbers that multiplies together to give me that composite number. So for 12, I can start off with 6 times 2 or 4 times 3. It says if these smaller numbers are both prime, then we're done. But if either one of them is not prime, then we're going to have to continue writing that number as a product of primes until we get to the point that the last branch, they're all prime numbers. So if I look at the way that I have broken 12 down into two numbers, 6 times 2, I look at the number 6. 6 is not a prime number, so I'm going to keep going. 6 breaks down into 2 times 3. Both 2 and 3 are prime numbers, so I stop. I look at the other leg, and I have a 2. It is prime, so I stop. So the prime factorization of 12 is 2 squared times 3. I'm going to look at another example of 12 in the way that I broke up 4 times 3. Well, I'm going to look at each branch. 4 is not prime, so I'm going to keep going. 4 breaks down into 2 times 2. That's prime, so I stop. 3 is prime, so I stop. I'm still going to end up with 2 squared times 3. You can see that the prime factorization of 12 does not change regardless of what factors I start with. That's what the fundamental theorem of arithmetic tells me. Every number has one unique product of primes. Okay, so find the prime factorization of each number. We want to show our work. We just did 12, but for our notes, we'll continue on. I'm going to use 4 times 3. I'm going to break 4 down into 2 times 2, and we can see we get 2 squared times 3. And you can see that I've typed in the answers there for you. Now let's look at 40. There's several different ways that I can multiply two numbers together and get 40. Some of you may start off by thinking about 4 times 10. Others might think about 8 times 5. Others might think about 2 times 20. Again, it doesn't matter what you started with. I actually broke it down into 4 times 10. Both 4 and 10 are composite numbers. They can be broken down, so I just keep breaking it down until they're all prime numbers. So you can see that 4 breaks down into 2 times 2, and 10 breaks down into 2 times 5, and then I get the last leg being all prime numbers. So that's 2 to the third multiplied by 5. That is the prime factorization of 40. And again, doesn't matter what factors I would have chosen here, my prime factorization either way is not going to change. It's going to be 2 cubed times 5. All right, so let's look at some more examples. Find the prime factorization of each number, show your work. So if I begin with 20 or 75, first thing that I think of is 25 times 3, and that's 5 times 5, and so I end up with 5 squared times 3. 88, I'm not sure how I broke it down in my notes, but I'm going to come up with the same prime factorization regardless. I would probably say 11 times 8. 11 is prime, so I would stop. 8 is 4 times 2. And 4 breaks down into 2 times 2. So I have 2 to the third times 11. What about 924? Okay, so we got a large number, so I'm going to look at my divisibility rules. I know that that is divisible by 4. How do I know that? Well, 4 divides into 24. So if 4 goes into 24, 4 goes into 924. So 4 goes into 924, let's see, that's 231 times. Let me double check because I'm doing this in my head with you. Okay. 231, just for my divisibility rules, if I add the digits up, 2, 3, 4, 5, 6, I know that it's divisible by 3. So let's take 231 and let's divide by 3. So what do we get? We get 77. And 77 divides into 7 times 11. These are both prime. And then I'm going to come up here and finish 4. That's 2 times 2. So let's see what we end up with. 2 squared times 3 times 7 times 11. All right, so let's look at 360. Several different ways that you can start here. I'm going to do 36 times 10. That's 6 times 6. Both are composite. I keep breaking them down. Then I'm going to break down 10 into 2 times 5. So we should end up with 2 cubed times 3 squared times 5. So this is prime factorization. Again, doesn't matter what factors that you use to get 360, my prime factorization of that number will always be the same. Let's talk about factors. Factors are the numbers that can be multiplied together to get another number. For instance, if I wanted to list all the factors of 10, I'm going to list all the numbers that multiplies together to give me 10. 1 times 10, 2 times 5. Those are the factors of 10. Notice I started with a small number. There's also a way to determine the number of divisors. So first of all, let's talk about divisors. All the factors of a number are its divisors. And there is a neat little theorem that we can do to determine how many positive divisors a number has. If P and Q are different primes, M and N are whole numbers, then P to the N, Q to the M has N plus 1 times M plus 1 positive divisors. All right, let's try to put this in simpler terms. If I'm trying to find how many positive divisors a number has. So let's look at an example. What if I wanted to find the number of positive divisors of 1 million? What you're going to do is you're going to break 1 million down into its product of primes. If you break 1 million down, you'll see that you get 2 to the 6 times 5 to the 6. All you have to do is take your exponents and add 1 to it. So, 6 plus 1 equals 7. And then the exponent on the 5 is also a 6. So 6 plus 1 is 7. You take your 2 exponents, you add 1 to both of them, and you multiply those numbers together. And that's how many divisors the number has. So 1 million has 49 different divisors.